Hey, Algebra 2, this is Unit 4, Lesson 2. We've got some exponential functions that we're working with. So homework tonight was 1 through 4, going to go over all of those. And I haven't done any of them, so, we're going to be, doing them from scratch, every single one. In 1990, the value of a home is $170,000. Since then, its value has increased by 5% per year. And yeah, we had a class where we talked about the average increase, and it actually is in the United States somewhere between 2 to 5% every year. So this fits within a natural range. What's the approximate value of the year of the home in 1993? So we're looking at this. We got 1990 to 1993. That's an increase of 3 years. And using our formula of the 170,000 times. Now, if it's increasing by 5%, we want to take 100% and add that 5% on to get 105%. But then we want to use the decimal form of that, 1.05. And we're using that for 3 years in a row. So, you take that in your calculator. 1.05 to the third power. And it really should be that fast to get an answer. So we're at $196,000 and $196,796.25. The cents don't really matter when we're talking about dollar amounts that big, but that is precision. All right, it says write an equation in function notation that represents the value of the home. Okay, so this is it. So we need, it says to use T for time. It doesn't really say anything. So I could use V for value of the home, or I could use H for home, the value of the home after T years. And it's that $170,000 times 1.05. But instead of a number here, we're using T. That's all. That's all. It should be pretty simple. And let's see, will the value of the home be more than $500,000 in 2020? Well, take 1990 and take that off of 2020. No, that's 1990. And so, 2020 minus 1990. And we got 30 years. So what are we going to do? We're going to use this equation, but we're going to be using it with 30 as the power. So 170 times 1.05 to the 30th power. So yeah, a lot of mortgages are 30-year mortgages. So this would be like somebody finally paid off their home after 30 years, and their house that was, oh my God, that's insane. Yeah, look at this. Their house that was $170,000 is now worth, that's insane, is now worth, let's turn that into a dollar amount, $734,730, $734,000. And I mean, honestly, that's this is why houses cost so much, is because they do follow this percent increase over time. So would your money that you had here, had you invested that in something else other than a house, would it be worth this much? I mean, because like annual inflation, increases somewhere around 2% is like what the government shoots for. You're actually better off, since this increased by 5% over those years. You would make more money by having it sunk into a house than to let it ride in the market. That's a crazy. That's like, $700,000. That's insane. All right, so the graph shows a wolf population has been growing exponentially. So right there's that key word. That means that we can use an exponential function. What was the population when it was first measured? We look at this. We look at the scale that each of these is 20. So this would be 100,000. Or let's see, it says just wolf population. So it's literally 100 wolves. All right, by what factor did the population grow in the first year? So 1 year is here. And if it went up 20, if we're up to 120 compared to original 100, that's a 20% increase. All right, so it would be, if we divide that, we get 1.20, but that means that the percent increase is 20%. So the math on that is pretty easy. And by what factor did the now this says by what factor. So technically we want this answer by 1.2. Yeah, that's actually the real answer we want for this one. So a 20% increase, but since they want the factor, that's the factor that we're multiplying by. Write an equation relating the wolf population W. Okay, so wolf population given number of years, it would be starts off with 100 and it's increasing by 1.2 each year. That's what we're looking for. All right, simple enough, simple enough. Moving on to number 3. We've got this graph. Here's a graph of an exponential function. Find the equation for it. Okay, so for this, we're gonna need to find some of these values here. And what we want is from one year to another. So right here, I can't tell where this, well, let's see. Can we tell where that really starts? If this is 200, look at, it's like, this would be 100. Is this 50? So let's see. I'm gonna start off. I'm gonna say that looks like it's 50. I'm gonna say that looks like it's 50. We can go with that as a starting value. So f of x would be starting off with 50. And as we go here, 50 doubles to 100, 100 doubles to 200, 200 doubles to 400. Yes, this is a doubling pattern. And so we could use that as our function. All right, on to the last one. The equation f of t equals, all right, represents the value of a car. Ah, right there, that's the value of the car. And this means that it's losing value over time after t years, and t is years. Okay, what do the numbers 24,500 mean? Well, that's the, okay, does it tell us the year? Okay, this is the value, how many dollars it was when it was purchased. Okay, that's the initial value. And this, well, if we had 100 minus what would give us 88%. So, you know, just thinking through that means it's losing 12%. Losing 12%. So that 0.88 means that 88% of its value remains each year. And that means each year. And that means that it's losing 12% each year. And what does f of 9 represent? Well, it doesn't tell us to actually find the value, but we should. F of 9, plug it into this equation, and that means we're using t's. So 2,400 times 0.88 to the 9th. So that means in 9 years after it's purchased, that $24,500 car is now worth $7,700. So 7753. Put a comma in there. Put a decimal place. Let's get our pennies. 72 cents. So what does it represent? It represents that after 9 years after it's been purchased, its value has depreciated down to $7,000, roughly. That's roughly how much they could sell the car for. Sketch a graph that represents, well, so we don't have a graph for this, and it says sketch. So sketch means we're allowed to kind of be rough with this. So f of 0, that would be 0 years, 1 year, 2 years. So they want us to find, well, let's take this. At 0 years, we know that it should be $24,500. Let's take the same equation and instead of 9 years, do 1 year. 21,560. That's its value after 1 year. Take the same equation, change that 1 to a 2. We get 18,972. 18,972. Now, how do we turn that into a graph? All right, first of all, I want a bit of a scale here. So 0 years, 1 year, 2 years. We need to hit some of these benchmarks. Looking at this, if I count, let's see, 5,000, 10,000, 15,000, 20, and 25. Counting by 5 seems to be a nice way to get up to this. It initially starts off with a value that's just shy of 25,000. After 1 year, it's a little over 20,000. After the second year, it's at, well, just under 19,000. So it's not the best graph, but you know, a graph that's depreciating like this. Now, if we scaled this out, this would eventually be like a curve that would, like, you know, curve out. But since we're only looking at these few years, it's kind of flat. All right, folks, that's honestly it. All right, so 10 minutes going over those 4 problems. Hope this made sense. The big thing is, can you set up the equations? Can you find that percent increase or decrease and use that as a decimal with the number of years to project an equation forward or backwards in time? Take care.